The drive to make things better, faster, smarter. It's just, well, it's fundamental, isn't it? Whether it's science or just making code run quicker.
Absolutely. And that's really what we're digging into today.
Yeah, we're looking at something called AlphaEvolve, a new coding agent from Google DeepMind. Sounds pretty advanced.
It definitely is.
Yeah.
It's pushing the boundaries in algorithm design using AI to actually improve the code itself.
Okay, AlphaEvolve. So break it down for us. What's the big picture?
Well, think of it like an AI that doesn't just understand code, but can rewrite it purposefully to make it better.
Better how? Faster?
Yeah.
More efficient?
Yeah, both. It
Yeah.
uses large language models, the AI tech that's so good with language,
Right.
but applies that skill to computer languages. It takes algorithms we already have and sort of evolves them, makes them more efficient, or finds totally new ways to solve problems.
Okay, so it's not just writing code from scratch. It's taking existing stuff and making it better, almost like evolution.
That's a really good way to put it. It's an evolutionary approach.
Yeah.
The LLM suggests changes, modifications to the code. Then those changes get tested automatically. Does this new version actually perform better based on criteria we set?
Oh, okay.
And that cycle, propose, test, learn, that's the evolution.
And that testing part, the automated evaluation, that sounds critical because LLMs can be confidently wrong sometimes.
Exactly right. You need that grounding. By running the code and measuring performance, you filter out the bad suggestions. You ensure the improvements are real. And what's really cool is that through this iterative process, you can end up with algorithms that look very different from where you started.
So it really could uncover genuinely new approaches, not just small tweaks.
Precisely. The paper shows it can be used for discovering completely new algorithms or just finding much better solutions where an algorithm is the key.
Now, AI and algorithms, I feel like we've heard about similar things before. Fun search, maybe. How is AlphaEvolve different?
Yeah, good question. AlphaEvolve definitely builds on ideas from FunSearch, but it's a significant step up.
How so?
Well, for starters, FunSearch mostly dealt with tiny bits of Python code, like single functions, very short.
Okay.
AlphaEvolve can handle whole code files, hundreds of lines, and importantly, it's not just Python. It can work with pretty much any language.
Wow. Okay. That's a big difference already.
Huge. And FunSearch needed really fast evaluations, like under 20 minutes. AlphaEvolve can manage much longer running evaluations, hours even, using parallel processing.
So it can tackle more complex problems where testing takes time.
Exactly. And while FunSearch generated millions of samples, AlphaEvolve often gets great results with fewer, maybe because it uses these much more powerful state-of-the-art LLMs with big context windows. They just understand more.
Right, more context.
Plus, AlphaEvolve can optimize for several things at once, multiple metrics. FunSearch was really focused on just one.
So it sounds much more powerful, more flexible.
I think that's fair to say. But there's a key similarity, too. It still needs problems where you can automatically score the solution, machine gradable.
Right, you need that objective measure.
Which naturally leads it towards maths, computer science, system optimization, areas where you can define success clearly.
Makes sense. So how much human effort is involved? Do we just press a button and it goes?
Not quite. Humans are still crucial, especially upfront. We define the what, meaning we set the goalposts, the evaluation criteria. What does better actually mean for this problem?
Got it.
We also usually give it a starting point, an initial solution. It doesn't have to be great, just something to begin with, and maybe some background info.
Oh, okay.
Then AlphaEvolve figures out the how, the actual code changes needed to reach that goal.
So we pointed in the right direction. How do we tell it which parts of the code to work on? Is it the whole file?
Good point. It's quite neat. You use special comments in your code, like #evolve block start and #evolve block end.
Oh, simple enough.
Yeah, whatever code is between those markers, that's fair game for AlphaEvolve to modify. The code outside provides the context and lets the evolve part run.
That seems really practical for integrating into existing projects. The paper also mentioned working at different levels of abstraction. What's that about?
Yes, that's a really interesting part. It's very flexible. Sometimes you want it to directly rewrite the raw code.
Okay.
Other times, maybe you give it a sort of recipe or a constructor function for building a solution, and you let AlphaEvolve evolve that recipe.
So it changes the instructions for building the thing, not the thing directly.
Exactly. Or it can go even higher level and evolve the search algorithm it uses to find solutions. Or even, get this, co-evolve both intermediate solutions and the search algorithm together.
Whoa, co-evolving. So the method it uses to find solutions gets better as it goes?
Precisely. And The research suggests different approaches work better for different problems. Like
Yeah.
if the solution has symmetry, evolving the constructor might be best. If it's more irregular, maybe evolving the search strategy itself is the way to go.
Fascinating. Okay, so we know the basics, the human role, the flexibility. Let's get into the engine room. How does it actually generate the improvements using these big language models?
Right, so it uses top-tier LLMs like Gemini 2.0 Flash and Pro and feeds them these really rich prompts. Big context windows are key here.
Meaning it can read a lot of information at once.
Exactly. And the prompts are customizable. You can give it problem details, math equations, bits from research papers,
Hmm.
explicit context.
So it's not just guessing.
No, definitely not. They also use something called stochastic formatting, basically, slightly varying the prompt structure to encourage, let's say, more creative outputs from the LLM.
Okay.
And the prompts often include results from past attempts, the code, the score it got, feedback.
Living from mistakes or successes.
Exactly. And one of the coolest bits is meta prompt evolution.
Meta prompt.
Yeah, the LLM actually suggests improvements to the prompts themselves, helping to refine its own instructions for the next round.
Huh. The AI is helping itself ask better questions. That's clever. And these diff blocks mentioned in the paper, what role do they play?
So when the LLM proposes a change, it often presents it as a diff. It clearly shows the old code, marked with something like search enchant or a diff, and then the new code between PROI and replace.
Like version control diffs. Makes
Yeah.
it easy to see the change.
Precisely. Very clear standard. But sometimes, for small changes or total rewrites, it might just output the whole new block of code.
And why use both Gemini Flash and Pro? Why not just the best one?
It's about balance. The Flash is faster, cheaper.
Yeah.
It lets AlphaEvolve explore lots of options quickly.
Yeah.
Breadth first, kind of.
Okay.
Pro is more powerful, maybe a bit slower, but it can generate more sophisticated, potentially breakthrough suggestions. Depth first.
So you get the best of both worlds. Lots of exploration plus deep dives.
That's the idea. An ensemble approach. Maximize throughput, but also capture those high-quality ideas.
Makes sense. So the LLM proposes a change in a diff block. Then what? How does it know if it's actually better? The evaluation step.
Right. The core is a function the user provides. You write a piece of code that takes the proposed solution and spits out a number, or maybe several numbers, the scores.
The metrics we talked about earlier.
Exactly. By convention, AlphaEvolve tries to maximize these scores. This could be checking a math proof, running a simulation, measuring speed, whatever matters for the problem.
And that score is the decider.
Mostly, yes. But there are some optional refinements, like an evaluation cascade.
Cascade.
Yeah, you do quick, cheap tests first. Only the ones that pass the easy tests move on to the slower, more expensive evaluations. Saves resources.
Smart filtering.
And sometimes they even use another LLM call just to get feedback on things like code simplicity or readability stuff that's hard to score automatically.
Interesting. Qualitative feedback almost.
Sort of. And crucially, all this evaluation can be run in parallel across many machines. That's essential for speed.
Right. Distributed computing. And you mentioned optimizing multiple scores, even if you only care about one main thing. Why do that?
Yeah, it's quite clever. Even if you just want, say, the fastest algorithm, also asking it to optimize for maybe memory usage or code length can help.
Ow!
The thinking is, it forces the system to explore a wider range of good solutions. By looking at the problem from slightly different angles, it might uncover more diverse, more innovative pathways that ultimately lead to a better result on your main goal, too. It prevents getting stuck in a local optimum too early.
Okay, that's subtle, but makes sense. Explore more widely. So you have all these potential solutions. They've been scored. How does AlphaEvolve decide which ones to use as the basis for the next generation of changes?
It keeps everything, all the generated solutions and their scores, in what they call an evolutionary database.
A library of attempts.
Exactly. And how it selects from that database is inspired by techniques like MAP elites and island models from evolutionary computing.
Okay. What does that mean practically?
It means it tries to balance exploration and exploitation.
Right.
It wants to keep trying new, different kinds of ideas, exploration, but also focus effort on refining the types of solutions that have already shown promise, exploitation.
The classic explore-exploit trade-off.
Right. You don't want to just keep polishing the best thing you found so far, but you also don't want to randomly jump around forever.
Yeah.
This database helps manage that balance.
And the whole thing runs on a big distributed system, you mentioned.
Yeah, it has to, given the scale.
Yeah.
There's a central controller managing things, lots of LLM sampler nodes proposing changes, and lots of evaluation nodes testing them out. It's all asynchronous and optimized for throughput, getting as many evaluations done per hour as possible.
Got it. Okay, we have a really good picture of the how. Now for the what. What has AlphaEvolve actually done? The paper highlights some big wins, starting with faster matrix multiplication. Why is that such a big deal?
Oh, matrix multiplication is foundational. It's everywhere in computing. Graphics, simulations, and especially training huge AI models like the ones we've been talking about. So finding faster ways to do it has huge implications. It's been a major research goal for decades, ever since Strassen found a faster way back in 1969. The challenge is finding these things called lower-rank tensor decompositions. Lower rank means fewer multiplications needed.
And AlphaEvolve made progress here, real progress.
Absolutely. Starting basically from scratch, just the problem definition and a standard algorithm, it discovered new, more efficient algorithms for 14 different sizes of matrix multiplication.
14. Wow.
Yeah. And the headline result is for 4x4 matrices with complex numbers. The best-known method, Strassen's algorithm effectively, uses 49 scalar multiplications. It stood for 56 years for the specific case. AlphaEvolve found a way to do it in 48.
48, one less, but after 56 years, that's huge.
It really is. It's the first improvement for characteristic zero fields in over half a century.
Amazing. And was it just a lucky guess, or did it involve significant changes?
Oh, significant changes. The paper shows it modified the optimizer, the initialization, the loss function hyperparameters, a whole series of evolved improvements, about 15 steps.
So it really built up the solution.
Exactly. And while these results came from a simple starting point, they also note that seeding it with some human expert ideas could boost performance even further. A real human-AI collaboration potential.
Incredible stuff. Okay, so fundamental computer science breakthrough. What about the pure mathematics side? You mentioned that too.
Yes, and this is maybe even more surprising in some ways. They applied it to over 50 open problems in various branches of math, combinatorics, geometry, number theory, packing problems.
Really diverse areas?
Very diverse. And the results, it matched the best-known human-discovered constructions in about 75% of cases.
Which is impressive on its own, rediscovering top results.
Right. But in about 20% of the problems, it actually beat the best-known results, discovered new state-of-the-art constructions.
It found new math. That's staggering. Can you give examples?
Sure. In combinatorics, it improved the upper bound for a classic problem called Erda's minimum overlap problem.
Oh.
In geometry, it tackled the kissing number problem. How many spheres can touch a central sphere? In 11 dimensions, the record was 592. AlphaEvolve found a construction for 593.
Wow. Pushing the boundaries.
Exactly. And there were others, improvements in autocorrelation inequalities, uncertainty principles, various packing problems like arranging points or polygons optimally.
How did it approach these math problems? Was it evolving proofs?
Mostly, no. For many of these, especially where checking a solution is fast, it focused on evolving search algorithms. It was given a time budget and the current best-known solution, and its job was to evolve a heuristic, a search strategy, that could find a better solution within that time.
So it learned how to search effectively for these specific problems.
Precisely. And it often came up with quite complex multi-stage strategies. Maybe one heuristic to find good starting points quickly, then another to meticulously refine them. Automating the discovery of good search methods is a big part of its power here.
And mathematicians were involved in suggesting problems.
Yeah, people like Javier Gomez Serrano, Terence Tao, suggesting challenging open problems. It really points towards AI as a potential collaborator in mathematical research.
Amazing. Okay, so fundamental CS, pure math. But it's not just theoretical. It's being used inside Google too, right, for practical stuff.
That's right. They've applied it to optimize parts of Google's own massive infrastructure. One example is data center scheduling.
Like deciding which computer runs which job.
Exactly. In their Borg system, they framed it as a complex vector bin packing problem fitting jobs with different resource needs onto machines. AlphaEvolve evolved a heuristic, a rule for deciding which job goes where. It found a surprisingly simple rule that actually outperformed the complex production system they were using.
No way. Simpler and better.
Yep. And deploying it recovered, on average, 0.7% of previously stranded compute resources across the whole fleet. That's a lot of computing power at Google's scale.
That's a tangible, massive impact. Why AlphaEvolve for this, not other AI methods?
They mentioned interpretability was key. Because AlphaEvolve produces code, engineers can actually read and understand the scheduling logic. For a critical system like Borg, being able to debug and trust the logic is vital. Easier than interpreting a complex deep learning model, perhaps.
Right, the black box problem. Makes sense. What else inside Google?
It helped optimize Gemini itself. specifically the low-level kernels, the software that runs matrix operations on Google's TPUs during training.
Optimizing the optimizer.
Kind of, yeah. Manually tuning these tiling strategies for kernels is super hard and takes ages. AlphaEvolve automated it
What was the result?
and averaged 23% speed up on those specific kernels, which translated to a 1% reduction in overall Gemini training time. Again, 1% is huge for these massive training runs.
And faster optimization, too.
Much faster. Months of human effort down to days. And this improved heuristic is now deployed, making Gemini training more efficient.
Incredible feedback loop. Gemini via AlphaEvolve improving Gemini, did it touch hardware, too?
It did. They challenged it to optimize the design of an arithmetic circuit in a TPU, described in Verilog, the hardware description language. Goal: reduce area and power. It found a simple code change, basically removing some unnecessary bits that worked. Validated by the TPU designers, it's Gemini's first direct contribution to TPU hardware design, communicated directly in the language engineers use.
Wow. Software improving hardware design. Okay, one more internal application mentioned optimizing compiler output. That sounds deep.
Yeah, very deep. They took the low-level code, the intermediate representation, or IR, generated by the XLA compiler for parts of flash attention.
Which is important for transformers.
Crucial. And also for pre-post processing code running on GPUs. This IR is usually just for debugging, and it's already heavily optimized by the compiler.
So a tough target.
Extremely tough. But AlphaEvolve still found optimizations, speeding up the flash attention kernel by 32% and the pre-post processing by 15%.
That's impressive on already optimized code.
It really is. And it suggests that these kinds of AI-discovered optimizations might eventually find their way back into the compilers themselves.
Amazing breadth of applications. So one last technical bit. The paper mentions ablation studies. What were they trying to figure out there?
Right. Ablation studies are where you systematically remove parts of the system to see how important each part is. They did this for the matrix multiplication and kissing number problems.
What did they remove?
Things like the whole evolutionary approach itself, the rich context in the prompts, the meta-prompting, evolving whole files versus just functions, using powerful LLMs versus weaker ones.
And the finding?
Basically, everything mattered. Each component they tested contributed significantly to the final performance. It wasn't just one magic ingredient.
So it really is the combination, the evolution, the smart LLMs, the context, the evaluation, all working together.
Exactly. It's the synergy of the whole system that delivers these results.
Well, this has been absolutely fascinating. A really deep look into AlphaEvolve. It feels like more than just an incremental step.
I agree. It shows a path towards AI, not just using tools, but genuinely improving and even discovering the fundamental tools of science and engineering.
So if we had to boil it down, what are the absolute key takeaways for our listener?
Let's say, 1, AlphaEvolve combines LLMs, evolution, and automated evaluation to make real discoveries. 2, it's achieved breakthroughs in fundamental areas like matrix multiplication and pure math. 3, it's already delivering practical, measurable optimizations in complex real-world systems, like Google's infrastructure.
Powerful stuff. And it leaves you wondering. We've seen AI get good at solving problems we set for it, but this feels different. AI discovering new ways to solve problems, new algorithms, maybe even new scientific ideas. So here's a thought for you, our listener. Where do you think this is headed? What fields might be completely transformed next by AI agents that can not just apply knowledge, but actually generate fundamentally new code, new algorithms, new solutions? Where does AI stop being just a tool and start becoming a genuine discovery partner?
That's the big question, isn't it? And if you want to dive even deeper into the specifics we discussed, the white paper is out there, and they've released code and notebooks for the math and matrix multiplication results too.
Definitely worth checking out. It really feels like we're seeing the start of something potentially revolutionary in how discovery and innovation happen. Thanks for joining us for this deep dive.